We are going to go through the next set of notes in our electrons packet. Today we're going to be focusing on our electron configuration, rules and notations. So we're going to be looking at something called an orbital diagram and also something called an electron configuration notation. Now I know these terms sound kind of new and maybe a little intimidating, right? Because we don't necessarily know what all of those words mean, but we are going to figure it out. Also, we have actually done this before. We've seen this before. So this isn't actually 100% new information. We're just going to formalize it. So just refresh our memories real quick. We learned last class that our atoms, our electrons in our atom are not arranged in little rings, right, around the atom like the Bohr model showed us. In this model, our atom was flat and our electrons orbited the nucleus like planets around the sun. Now we've now learned that atoms are not flat. We knew that one already, but we also the electrons are arranged a little bit more complicated, right? The arrangement is a little bit more complicated than the Bohr model suggested. Excuse me. But we learned last class that they have these things called orbitals. And orbitals are the areas in the atom where electrons are most likely to be found. So this isn't where you're definitely going to find an electron, but this is an area with really high probability of an electron. Right? Theoretically, the electron could be temporarily someplace else, but these areas are most likely where you're going to find an electron. So we have 4 different types of orbitals. They're called S, P, D, and F, right? And we learned that each orbital can hold, there's 2 electrons, right? And they sometimes come in sets. So when you see an S orbital, you only see one of them. When you see a p orbital, they actually come in sets of 3. D orbitals come in sets of 5, and F orbitals come in sets of 7. Now we also learned that they come in different shapes, so they don't all look the same. And we're going to be doing an activity later, probably when we, maybe after break, but we're going to be doing an activity later that involves actually seeing how these orbitals fill and looking at the three-dimensional model and seeing how these start to fit together a little bit more. And yeah, so that means that also every time an S orbital happens, you're only going to have one of them, and that's going to hold 2 electrons. Every time we have a p orbital, it's going to come in a set of 3 of them, and so that p sub-level will hold 6 electrons. D's come in sets of 5, so hold a total of 10 electrons. F's come in sets of 7, and so hold 14 electrons. Now you'll also notice in our orbital filling order down here, they don't go in order. You might think you have 1s, 1p, 1d, 1f, 2s, 2p, 2d, 2f, etc. And that's not how it goes, right? We actually have 1s, 2s, and then the p's pick up. The D's don't happen until after 4S, and you don't get 4D right away. You actually get 3D. And the F's don't pick up until the 6th level, right? The 6th energy level is when the F's pick up, and it's actually a 4S, not a 4F, not a 6F, which I know is a little confusing. But if we look on the next page, we're going to see this right here. And we see that, let's zoom in on this a little bit more. We see that the periodic table actually matches it pretty well with this idea of this orbital structure. So our s orbitals, right, each hold 2 electrons, 1, 2, right? So this section of the periodic table houses our s electrons. So anything in our alkali metals or alkaline earth metals, their final electrons fall in an s orbital. Anything in our other metals, our metalloids here in the zigzag, our other non-metals, our halogens, and our noble gases, except for helium, all of their last electron is actually going to be in a p orbital, right? So we can actually see p orbitals hold 6 electrons. We have 1, 2, 3, 4, 5, 6 across here. Our transition metals, these all have their final electron in a d orbital. And the fact that they have this d orbital actually is the reason that they act the way they do. Transition metals can have a lot more possibilities in some ways than other atoms because the way that they bond with other atoms isn't constant, and that is in part due to that d orbital. Okay, so then we lastly have the f orbitals. Now, you'll notice these are our lanthanide and actinide series, right? So these guys are the ones that are offset at the bottom, and these are our f orbitals. So these guys, all of these elements here, have their final electron in an f orbital. All right, so now we've done that quick review, let's go ahead and look at the new stuff. So as we saw in the electron configuration POGL with the little houses, hopefully you remember that, we've actually done this before, all right? So this is not brand new. So these are actually the same rules that we saw in that POGL. Now, we looked at this in two different ways, right? We saw this in the form of the little houses, but then we also saw this in an actual orbital model that looked something like this. All right, so let's go ahead and look at the rules quickly. So remember, these are just another way to represent the atom, and in this case, we're really focusing on the arrangement of the electrons. So our Bohr model focused both on the nucleus of the atom and the electrons, thinking about the energy levels of the atom, and our orbital theory really is ignoring that nucleus and focusing only on the electrons and their precise location, as close as we can get to it, in our electron cloud. So let's go through the rules. So our first one is our lowest energy orbitals are filled before our higher energy orbitals. So from the POGL, we learned that 1s is the lowest down, has the least amount of energy, and then 2s, and then 2p, and then 3s, and then 3p, etc. Right? If you ever forget the order, it's right here. You can go look here. Again, we're on page 3 in our packets, by the way. Okay, so our next rule is, right, so this one is correct and not that one. Our next rule is that every time an orbital gets an electron, right, you have to make sure that every orbital in a group has one electron before you double up. So the rule from our POGL, right, is that every bottom bunk needs a person before we get another bunk. So just as a quick note, right, because we maybe have forgotten from the POGL, or maybe you weren't here, this right here, this box represents an orbital. This set, right, this is an energy level or a subgroup. Also can call it a sub-level because you'll notice that there's a 2 here and a 2 here. We often say that they're part of the same energy level, even though one has higher energy than the other. And then each of these here, each arrow represents electrons. Right? This is 1 electron. And then this is 2 electrons with opposite spins. So this isn't spins like a planet spins, but spin is a word that is used to describe a very specific property of an electron, but it isn't actually like spinning on an axis like the planet. Right, or like spinning a basketball on your fingertip. It's a little bit different than that. All right, so here we see that each orbital needs to get 1 electron before we double up, right? So we have an empty orbital here. This cannot happen, right? We don't want empty orbital, right? When others in the group are full. Okay, and so lastly we have this rule here. Only 2 electrons of opposite spins can occupy an orbital, right? So that means that this one, they're going in the same direction. That is not correct. And this one, they're going in opposite directions. That one is correct. It also means that we cannot have 3, right? Cannot have 3. They can only hold 2. Now, you could have a situation where you just have 1. That is also okay. But only if it's the highest energy orbital can you have 1. Like, we don't have a situation. So like right here, right? This is okay. That's acceptable. All right, so we can also, there are formal names for these rules. Our first rule here is the off-bow rule. You fill from lowest to highest energy. And also, right, you can't skip. Right, you can't skip orbitals. And this also means that the lowest one needs to be full before you move on. All right, Hund's rule is the second. Each orbital of the same sublevel must be filled with 1 electron before doubling up, right? So you want to have each bottom bunk before the top bunk. And so here's an example here. And then finally, the Pauli exclusion principle. So the electrons in the same orbital must have different spins, right? Arrows must be going in opposite directions. All right, so this is where we're really going to be taking some notes. Hopefully you all got a little bit of this down. And we're going to go ahead and talk about drawing orbital diagrams and electron configuration notations. So our orbital diagrams, for both of these, we're going to do the example of carbon. So we're going to use carbon as our example. Okay, so to find our orbital diagram, we're going to draw this first. So this is a lot of drawing here. So we're going to do our orbital diagrams first. The very first step that we need to do is we need to find out how many electrons we have. Right? And to do that, we need to look at the atomic number. Because the atomic number is going to tell us the number of protons, which then tells us the number of electrons. So for carbon, if we look at the periodic table, right here, we see its atomic number is 6. That means that it has 6 electrons. Now, this is going to tell us how many arrows to draw. So maybe you're looking at this diagram above and you're like, how do we come up with that many arrows? This tells us the number of arrows that we need to draw. All right, so next is we're going to draw our diagram. Okay, so you are mostly going to be given the framework for the diagram and you will just need to fill in the arrows. But when we get to a little farther along, you might need to draw it. So I'm going to show you how to do that. So you're going to draw your diagram. That is our next step. And you're going to draw the diagram. You're only going to add new sublevels when the previous is full. Okay, and we have to make sure that we're also following all of the rules up here. Okay, so let's go ahead and draw our diagram. So we're going to start off with the 1s level because that is the lowest energy. And each orbital can hold up to 2 electrons. And before we can add another one, we got to have the first one full. So we're going to draw an up arrow and a down arrow. And that one is now full, and so we can add a second level. So now we are adding our 2s level because that is next in the order. The order is right up here as well as on page 2. So we have a total of 6 electrons, so we got a few more to add. All right, so we're going to add our next 2 electrons, 1 and 2. All right, so now we have our 2s level, sorry, 2p level. Because it goes 1s, 2s, and now we have our 2p. And you'll notice I drew 3 lines for our 2p because there are 3 orbitals in the 2p level. Now, we currently have 4 electrons written down, and we need 2 more. So many of y'all are going to be like, okay, 1 and 2, and done. But it's not, right? Because of Hund's rule. Hund's rule here, or rule number 2, says that you need to put 1 electron in each orbital first, and then you can place the second. That means that before we double up, each one of these needs to have 1. But that's more electrons than we have. enough. We only have 2 more. And so we're going to draw up and up. And that is done. This is the orbital diagram or orbital notation for carbon. Ta-da! Okay, so now we are going to do the electron configuration notation. Now you have also done this before, because this, or seen it anyway, this is the manager's code from the POGIL. So in order to do our electron configuration notation, what you're going to do is you're going to take this orbital diagram, all right, and you're going to rewrite it. And now you're not going to rewrite it exactly the same, right? Because this is going to look different. And this is the way you would convey this information about electron placement if you were writing it in a sentence, right? This is a good picture to help you think about things, but if you were to write it in a sentence, you would use your electron configuration notation. So you're going to rewrite it. Whoops, skipping ahead. You're going to rewrite it, but you're going to represent the electrons as exponents instead of arrows. Okay, so we're going to rewrite this, but as an electron configuration. So we're going to start off with our 1s. 1s. Now, again, we're going to replace the arrows as an exponent. So in our 1s level, we have 2 arrows. So we're going to write the exponent 2. In our 2s level, we have 2 arrows. So that means we're going to write a 2. In our 2p level, we have 2 arrows, 1, 2. So we're going to write a 2. All right, and that's it. This is how you do it. So let's just go through quickly what this stands for, right? So if we remember the big number right here, this is our energy level, right? So that's our energy level. Okay, and next we have our S and P. So I'm going to go and highlight our S and P, just do a little color coding here. If you want to color code on your papers, I always encourage it. If you're seeing this in the classroom, I'll help you get some color coding supplies. So what I highlighted in purple here, the S and the P, these are our orbital types. And last but not least, we have our superscript numbers, right? These are our number of electrons. Great, so I'll leave this up for a minute, and then we're going to do one together on the top of page 11. We're going to do one on the top of page 11 together. Hopefully if you needed to pause, you paused. And we're going to do top of page 11 together. Now, you'll notice there is more on this worksheet than we are going to do, because we haven't talked about everything yet. And that's okay. That just means we're going to revisit this worksheet multiple times, which is also kind of cool. So it'll allow us to look back on our work and use it to increase our understandings, which is actually ideally what we're doing all the time. So we're only going to do this section, right? In each of these boxes, we're only going to do this top section. we're not going to do that bottom line that says valence electron, Lewis dot diagram, and number of bonds. We're going to come back to that later. All right, so for our first element, we have sulfur. So we first need to find out how many electrons we have. So if we go to the periodic table and find sulfur, sulfur is right here. It is a non-metal. We look right here and we can see it's element number 16. Element number 16, that means it has 16 protons, and therefore also, hopefully you already guessed it, 16 electrons. Zoom in a little bit more here. All right, so let's go ahead and finish filling this out. So our orbital notation, we know that we have 16 electrons. That also tells us that we need 16 arrows. Right, 16 arrows. 16 electrons, 16 arrows. So we're going to make sure we're filling this out using all of our rules that we talked about, starting with the lowest level first. We're going to do an up arrow and a down arrow. Now remember, we got to fill in the lowest level first, and the entire level needs to be full before we can add another one. So now that our 1s is full, because it has 2 electrons, we're going to go on to our 2s. Remember, each line can only hold up to 2 arrows. Now we have 16 electrons, we got a ways to go. So now we're going to add in our 2p, because we've only used 4 of our 16. Now I'm going to show you all something that I encourage you to do because it takes no more time, but is going to save you time in the long run because you'll know you've done it correctly. So a lot of y'all are like, okay, well 2p, it's going to be totally full, so I'm just going to go up, down, up, down, up, down. Except that you're not. Now you're not going to do that because that's not how they fill. I want you to practice every time you do these, even if you know that a whole section is going to be full. Still practice the order of adding them, because then when it's not full, you will not have messed it up. So that means that when we're filling our 2p, we go up, 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 right? So each line has 1. Each orbital has 1 electron in it. And then you double up, down, down, down. Now that took no more time than doing it the first way, but it's gonna prevent you from messing up later. Okay, so that is 10 electrons because we have 6 plus 4. So that's 11, 12, and now we have 4 more. So again, this is where that order really matters, because if you were doing the up, down, you would probably end up doing this for our last 4. And that is not correct, because we would have 2 full orbitals and 1 empty one. That is just not going to happen. It is not energetically favorable. So instead, we do this. 1, 2, 3, 4. Right? And to some people you might think, oh, well, but it's 4 electrons in the 3p, whatever. But it actually is really, really important in terms of knowing how the atom interacts with others. You actually need those 2 unpaired electrons. All right, so last thing, we are going to take this and we're going to convert it to an electron configuration. So again, right, you take your labels from our orbital model, or orbital diagram. Right, carry them down, 1s, 2s, 2p, 3s, and 3p. Now again, instead of arrows, we write the number of arrows as a superscript number, also known as an exponent, right? So we have 2 electrons in our 1s, 2 in our 2s, 6 in our 2p, 2 in our 3s, and 4 in our 3p. And that is it. Go ahead and try the other ones on page 11 and 12.